Assalamualaikum warahmatullahi wabarakatuh and good afternoon to all. Sorry for a bit late to upload this video. So we want to continue on chapter 7, which is about steady state errors. Okay, so we have looked before this about transient response and all of those. Now we want to look at the steady state once it's reached that steady level. So okay, so if you could recall, based on chapter 1, we saw that control system analysis and design focus on 3 specifications. There's transient response. In chapter 4, we did that transient analysis, and then there's that stability, which is in chapter 6. We look into the RH criterion, and then the next part we want to focus is this steady state errors, which is covered in chapter 7. So basically, in terms of the analyze and design and test, it is covered in the 6th step. So this one is where we're up to. Okay, we want to analyze the response. We want to design to meet the requirements and specifications, certain specifications. Okay, so what is steady state error? Okay, from here we could see that it's basically the steady state error is the difference between the input and the output for a prescribed test input as t approach infinity. So if you could see here, okay, just the same example that we have looked in chapter 1. We have to look into the elevator response, and let's say the user press on number 4, and you could see the blue line is the response of that elevator. Okay, so from here to here is the transient response, which was covered in chapter 4. You could see there's first order and second order in that chapter, but there's also a higher order than second order. But it's not covered in the syllabus, so you don't have to worry about that. But bear in mind, you have to know how to analyze that the first order response, the first order and the second order response and specifications. And then we have a look into that one. Then for this part, we want to see that steady state. So if you could see here, the user press on number 4, but the elevator goes only until here. It doesn't reach exactly on the level 4, meaning that it might be the slight, it's not that reach a certain level. So you could see here there's a slight small steady state error. So this is what we want to analyze. It's the difference between the input and the output for a prescribed test input as t approach to infinity. So to do that, there's test inputs that are used for steady state error analysis and design. So to determine whether your system can reach at a certain level, we need to test it. There's a few test inputs that we can put into it. Okay, so this is that test inputs. Okay, you have 3 options here. The waveform, it can be either ramp waveform, where this one is a constant at a certain amplitude. It could be a step input where it rise proportional to the time, or it can be a parabola input. So the physical interpretation of this waveform is that basically the ramp describes the constant position. Okay, just like the elevator response, where it reached to that certain level, to that position. Okay, So it represents a stationary target. And then how about the step input is basically describe the constant velocity. So the target is moving, but it's at the constant velocity. So it represents a constant velocity target. And then the last one is a constant acceleration, where you could see that the target represent the accelerating target. So it accelerates a little bit. It accelerates at a constant uh, acceleration. Okay, so basically these three describe a certain target. If you could remember the time function of each of these, the ramp is basically RT equals to 1, okay, or it, because in this case the level here is represent 1, but it can be any amplitude, but in this case it's 1. Or it can be if it's this one step, your RT is equals to T, because it's linearly increase as time. And the last one is a parabolic, which it is it's squared, though it rise with its squared T. Okay, so each of these, once you take the Laplace transform, you will get this form. Okay, remember, if you could look at into the Laplace transform table. So basically the time function is 1 over s of 1, and this one 1 over s squared of t, and 1 over s cubed for this one. Okay, so now let's have a look at this example. Okay, so let's say you have that tracking system. So this is your system. Okay, and you have to test it first. Either it's working or not. Is your tracking system is working? So what you do is that you take all the test inputs. You have to consider those those test inputs. So if you want from your what do you call this satellite? No, sorry, the antenna. Let's say you want to observe the satellite in a geostationary orbit. Okay, so you can use that step inputs that represent a constant position. So it's a constant position. Thus, it is, hang on there. So the step inputs are useful in determining the ability of the control system, this control system, to position itself with respect to a stationary target here. Okay, so that's for step inputs. How about a satellite that is orbiting at constant velocity? So in this case, we can use RAM inputs, which represent constant velocity inputs to a position control system by their linearly increasing amplitude. So a position control system that tracks a satellite that moves across the sky at a constant angular velocity. So this one, RAM input, is for, in this case, where it is constant velocity. How about the accelerating missiles, where it accelerates, it doesn't have that constant velocity, it will accelerate. So in this case, parabolas are suitable, whose second derivative are constant. So this represents a constant acceleration inputs to position control system. So those are the example where you could see to identify, to make sure that this tracking system is working. So there are test inputs that you can consider to test that stability and the steady state error, or the response itself. Okay. Now let's examine the concept of the steady state error. So I want to give you an example here. So let's say you have that input, okay, a step input, which is this line, and then there are a certain possible output that you can see from this figure. The first one is the output 1. So the output 1, it goes to the transient response and it reach that 0 steady state error. But in the case of output 2, it goes to that transient response, but it reach at a certain level where you could see there's a steady state error. It is at a certain finite value. You have that finite value. So that are the possible output of a step input. Okay, so it might be there's no reach the steady state error is 0, but at the same time it can be a finite value of a steady state error. Okay, so that in that case is step input. Another one that I would like to give an example is the ramp input. Okay, you have that ramp input, so this is your ramp input. Okay, the ramp equals to t, so it linearly increase. Okay, so in this case the first output, it can be you could see this line. Okay, it reaches at a certain slope and then it reaches to 0. Okay, so this is your steady state error is 0. But there's another possible output is that you have that a similar slope to the input, but you have this vertical difference. So this is considered as your finite steady state error. Okay, so you to calculate that difference is that you look at the vertical of the input and the output difference. Okay, that's the possible output 2. And another possible output is that the output 3, this one, the slope is completely different and it doesn't reach to the input. It doesn't reach to that input. It deviates and it goes to infinity. So in this case, the steady state error is infinity. So basically the input, the test input are different. Even you have the same system, like the last time you have that tracking system, but once the input are different, it will give different response according to the input that we consider. Okay.